Hello students, in today's lecture we are going to learn about mechanical properties of fluids, NCERT section 9.1 to 9.2.1. We will also solve an example 9.1. This is disclaimer, strategy for competitive exams. So first, master Pascal's law, pressure concepts and fluid density calculations. Next, learn uh, Bernoulli's principle and equation applications. Practice problems on surface tension, viscosity, and capillarity. Understand streamline and turbulent flow. Focus on manometer problems and Stokes law calculations. Solve numerical problems for Archimedes principle and buoyancy. Solve problems from past year JEE and NEET papers. For recommended books, please visit our website forum.puta.ai for comprehensive book recommendations and expert guidance. Learning objectives. By the end of this lecture, you will able to understand the fundamental differences between fluids and solids in terms of their physical properties. Learn about pressure and its relationship with force and area, including Pascal's law for fluid pressure, and comprehend how pressure is measured and calculated in fluids at rest, including the concept of density and its units. So in today's lecture, we will cover first 9.1 introduction, then 9.2 pressure, and we will solve an example 9.1, and last 9.2.1 Pascal's law. Now we are going to explore the fundamental properties and behaviors of fluids compared to solids. Let's start by defining what we mean by fluids. Both liquids and gases can flow, which is why we refer to them collectively as fluids. This ability to flow is a key characteristic that sets them apart from solids. Fluids differ from solids in their ability to flow. So in the figure, you can see the flow of liquid compared to ice cubes in a container. This visual helps us understand that while solids like ice maintain their shape, liquids adapt to the shape of their container, demonstrating that fluid nature. Alright, so it means fluid can flow. Alright, whereas solids maintain their shape. It's important to recognize that Earth is surrounded by fluids. The air we breathe and the vast water bodies covering 2/3 of the planet's surface are both examples of fluids. This highlights the significance of fluids in our environment and their role in various ecological and atmospheric processes. So, living beings, including mammals and plants, depend on fluids for survival. Whether it's through the circulation of blood in animals or the transport of nutrients in plants. This dependency underscores the vital role fluids play in sustaining life on Earth. Now, let's start by asking ourselves, how are fluids different from solids? This question will guide our exploration of the unique properties of fluids. One key difference is that fluids do not have a definite shape of their own, unlike solids which maintain a fixed shape. Fluids adapt to the shape of their container. The specific characteristics that distinguish fluids from solids are: first, shape adaptability. Fluids take the shape of their container as shown in the figure. Here, fluid in a container. Notice how the fluid conforms to the container's shape, illustrating adaptability. Next, flow capability. We have flow capability, alright. So fluids can flow under the action of very small shear stress. This means that even a slight force can cause a fluid to move, unlike solids, which require more force to change shape. And next, volume behavior. Solids and liquids have relatively fixed volumes, meaning they don't expand to fill a container. Alright. However, gases which are also fluids will fill the entire volume of their container, demonstrating their unique behavior. And next is compressibility. Solids and liquids have much lower compressibility compared to gases. This means that gases can be compressed much more easily. Alright. These properties make fluids essential and unique in both natural and biological systems. Understanding these differences helps us appreciate the role fluids play in our world. Alright. So, the fundamental characteristics are shape adaptability, flow capability, volume behavior, and last, compressibility. Alright. Now, let's start by considering what liquids and gases have in common. Both are classified as fluids. But what does that mean in terms of their properties? We will explore this by looking at several key characteristics. So, both liquids and gases share several important properties. These properties helps us understand why they behave differently from solids. So first is resistance to shear stress. Alright. So notice how both liquids and gases offer very little resistance to shear stress. This means they can easily change shape when a force is applied. Unlike solids which maintain their shape, fluids flow under stress. Next is molecular motion. Alright. So molecules in both liquids and gases have significant kinetic energy, which allows them to flow. This motion is what enables fluids to adapt to the shape of their containers. Another important property is pressure transmission. Both liquids and gases can transmit pressure uniformly in all directions. Alright, this is why, for example, when you squeeze a balloon, the pressure is felt evenly throughout. And last, viscosity. This is very important concept. So both liquids and gases exhibit internal friction during flow and known as viscosity. This internal friction affects how easily a fluid can flow, with higher viscosity indicating more resistance to flow. Alright, now uh, let's start by considering how the volume of a solid, liquid, or gases depends on the stress or pressure acting on it. Alright, so when we refer to the fixed volume of a solid or liquid, we are talking about its volume under atmospheric pressure. Alright, keep in mind that this fixed volume can still change under different pressures. It means if we applied the pressure, the volume will be changed. Next, let's look at the difference between gases and solids or liquids. For solids and liquids, the change in volume due to external pressure is relatively small. This means they are less compressible compared to gases, which can expand or contract significantly with pressure changes. So, consider the shearing stress required for fluids. It's about a million times smaller than that for solids, which explains why fluids flow so easily. This low resistance to flow is what makes fluids unique, and it is a fundamental reason why they behave differently from solids. Alright, now we are going to explore the concept of pressure. So, a sharp needle can pierce our skin when pressed against it. This is because the needle has a very small contact area, which increases the pressure exerted on the skin. This example helps us understand how pressure works in practical terms. When we press a blunt object like the back of a spoon against our skin with the same force, our skin remains intact. This is because the larger contact area reduces the pressure. It means pressure depends on area. Now imagine if an elephant were to step on a man's chest. The immense force over a small area would cause the ribs to crack. However, if a circus performer places a large, light but strong wooden plank across their chest first, they can avoid injury. The plank distributes the elephant's weight over a larger area, reducing the pressure on any single point. This demonstrates how increasing the contact area can uh, mitigate the effects of force. These examples show us that both the force applied and the area over which it is distributed the crucial in understanding pressure. It's not just it's not just about how much force is applied, but also where and how it's applied. The smaller the area on which a force acts, the greater the impact or pressure. This impact is what we define as pressure. Our everyday experiences teach us that both the force and its coverage area are important in determining pressure. This foundational concept will help us as we delve deeper into the mechanical properties of fluids in future lessons. Now, let's start with the historical context. The systematic study of pressure began with Pascal, a French mathematician and physicist. His work in 17th century laid the groundwork for modern hydraulic engineering. So the concept of pressure was systematically studied by Pascal, 1623 to 1662, whose pioneering work on fluid pressure laid the foundation for modern hydraulic engineering. Alright. His observations about pressure transmission in fluids revolutionized our understanding of mechanical advantages in machines. Now, uh, let's start by defining pressure. Pressure is the force exerted per unit area on the surface of an object. Alright. When an object is submerged in a fluid at a rest, look at figure 9.1a. The force exerted by the liquid in the beaker on the submerged object or on the walls is normal to the surface at all points. So when object is submerged, the force is always perpendicular to the surface at all points. This perpendicular force is what we refer to as pressure. The figure 9.1 also shows an idealized device for measuring pressure, which is shown in figure 9.1b. An idealized device for measuring pressure. Alright. Now, uh, let's start by looking at how force is applied in fluids. Notice that the force exerted by fluid is always normal or perpendicular to the surface of an object. This is crucial because it means the force is directed straight out from the surface, as shown in figure 9.1a. This perpendicular force is what we measure as pressure. So look at figure 9.1a. So small object and the forces are applied from all directions. So this is so because if there were a component of force parallel to surface, the object would exert a force back on the fluid in the same direction. According to Newton's third law, this would cause movement which does not happen when the fluid is at rest. This is an important point because it helps us understand why the force must be perpendicular. In a fluid at rest, there can be no parallel flow, reinforcing the idea that pressure acts normal to surfaces. Since the fluid is at rest, parallel flow cannot occur. Therefore, we conclude that the force exerted by a fluid at rest must be perpendicular to the surface it contacts. This is a fundamental principle of fluid mechanics and is clearly illustrated in figure 9.1a. Understanding this helps us grasp how pressure is distributed in fluids. So, uh, let's start by looking at the normal force exerted by a fluid at a point. So, look at figure 9.1a. How the force exerted by the liquid on the submerged object or the walls is always perpendicular to the surface. This is a key characteristic of pressure in fluids as it acts uniformly in all directions. So, an idealized form of one such pressure measuring device is shown in figure 9.1b. This device helps us visualize how pressure can be measured in a fluid. It's important to understand how such devices work because they allows us to quantify the pressure exerted by fluids in various applications. So the device consists of an evacuated chamber with a spring. Listen carefully. Evacuated chamber with spring. This spring is calibrated to measure the force acting on the piston. This pressure measuring device is placed at a specific point inside the fluid. The inward force exerted by the fluid on the piston is balanced by the outward spring force. Alright, this balance allows us to measure the pressure accurately. Understanding this balance is essential for interpreting pressure readings and applying them in real world scenarios. Now, uh, let's see this mathematically. So, we define average pressure. If F is the magnitude of the normal force on a piston with area A, then the average pressure P average is F divided by A. Alright, this relationship helps us quantify because in a practical way, the figure 9.1a here illustrates how pressure is exerted by a fluid on the submerged object or the walls of a container. So the average pressure P average is equal to force upon area. Alright, so in the limiting sense, or we can say uh, consider what happens as the area becomes very small. In that case, area approaches zero. We can define pressure more precisely. This concept is important for understanding how pressure can vary at different points on a surface. So, the precise definition of pressure is given by the limit as the area approaches zero. So, P equal to limit delta A approaches zero. Delta F divided by delta A. Alright, it shows us that the pressure is a force per unit area in an infinitesimally small region. Now, let's start by looking at some key properties of pressure. So, pressure is a scalar quantity, not a vector. It means it has only a magnitude. There is a no direction. Dimensions m L inverse t raised to the power minus 2. SI unit Newton per meter square or Pascal, named after Blaise Pascal. Now, let's start by looking at some common units of pressure. Pressure is a measure of force applied over an area, and it's important to know the units we use to express it. So the first unit we will discuss is the atmosphere. Atmosphere. as ATM, abbreviated as a ATM. 1 atmosphere is equivalent to 1.013 into 10 raised to the power 5 Pascal. This is a standard unit of pressure. Next, we have the bar. 1 bar is equal to 10 raised to the power 5 pascals. This unit is commonly used in metrology and engineering. It's a slightly less than an atmosphere, making making it a convenient unit for many practical applications. And last is torr. 1 torr is equal to 133 pascals. This unit is named after uh, Torricelli, an Italian physicist. Now let's shift our focus to understand important concept density. Density is a complementary concept to pressure and helps us understand how mass is distributed in a fluids. So for a fluid, density is defined as the mass of the fluid divided by the volume it occupies. This relationship is fundamental in fluid mechanics and helps us predict how fluids will react under various conditions. The equation for density is rho equal to mass upon volume. This equation is very important. Understanding this equation allows us to calculate the density of any fluid, which is essential for solving many physics problems. Now, let's start by discussing the properties of density. Density is a fundamental property of uh, matter that helps us understand how mass is distributed in a given volume. Here we see the dimensions of the density, which are mass per unit volume represented as m L raised to the power minus 3. This notion helps us understand the relationship between mass and volume in a mathematical context. SI unit of density is kilogram per cubic meter. This unit is standard in scientific measurements and allows us to compare densities across different substances. Behavior. So let's look at the behavior of density in different states of matter. Solid state, liquid state, and gaseous state. So liquids are largely incompressible, meaning their density remains nearly constant. It never be changed. In contrast, gases can have significant density changes with pressure. This distinction is crucial when studying fluid dynamics and understanding how fluids behave under different conditions. And last, reference value. Water at 4 degrees Celsius has a density of 1.0 into 10 raised to the power 3 kilogram per meter cube. This is a standard reference point used in many calculations and experiments. Now, uh, let's take a let's take a look at table 9.1, which lists the densities of common fluids at standard temperature and pressure (STP). So, fluid: water, sea water, mercury, ethyl alcohol, whole blood, air, oxygen, hydrogen, or interstellar space. So as we examine the table for here, we observe the differences in density among various fluids. For example, mercury, which is much denser than water, with a density of 13.6 into 10 raised to the power 3 kilogram per meter cube. This means that mercury will exert more pressure than water at the same depth. Alright, so understanding these differences is a key to predicting how fluids will behave in different scenarios. Alright, So water, the density is 1 into 10 raised to the power 3 kilogram per meter cube, and interstellar space approximately 10 raised to the power minus 20. Example 9.1. The two thigh bones, each of cross-sectional area 10 centimeter square, support the upper part of an human body of mass 40 kilogram. Estimate the average pressure sustained by the femurs. So here you have to find out the average pressure. All right, let's see the solution. So let's begin by identifying the given information. So cross sectional area of each femur, A1 equal to 10 centimeter square. Mass supported M equal to 40 kg. Acceleration due to gravity, 10 meter per second square. Total cross sectional area of both femurs, 2.0 into 10 raised to the power minus 3 meter square. So force acting on the femurs, so F equal to mg. All right, and F equal to 40 into 10, because M equal to 40 kg and G equal to 10 meter per second square. So now that we have the force, we can calculate the pressure. All right, so F is equal to 400 Newton. So now average pressure. So the formula for average pressure, P average is equal to force upon area. So let's substitute the given values into the formula. We have a force of 400 newtons and an area 2.0 into 10 raised to the power minus 3 square meters. By plugging these numbers into the equation, we can calculate the average pressure. So after performing the calculation, we find that the average pressure is 2.0 into 10 raised to the power 5 Newton per meter square. Therefore, the average pressure sustained by the femurs is approximately 2 atmosphere. Alright, this comparison to atmospheric pressure helps us appreciate the strength and uh, resilience of our bones under normal conditions. Physical interpretation. This pressure is about twice atmospheric pressure, demonstrating the significant stress our bones must withstand even during normal standing. 9.2.1 Pascal's law. Now we are going to explore an important concept in fluid mechanics, that is Pascal's law. So let's start by defining Pascal's law. According to this principle, when you apply external static pressure to a confined liquid, that the pressure is distributed evenly throughout the liquid in all directions. This means that no matter where you apply the pressure, it will be felt equally everywhere in the liquid. So to visualize this, take a look at the figure 9.2. It shows how pressure is transmitted through a prismatic fluid element in equilibrium. Alright, notice how the pressure is evenly distributed, which is a direct proof of Pascal's law. This concept is fundamental in understanding how fluids behave under pressure. This observation was first made by the French scientist Pascal in 1653, which is why it's named Pascal's law or Pascal's principle. Now let's consider the implications of Pascal's law. This principle is essential for the functioning of hydraulic systems, which are used in various applications like car brakes and heavy machinery. Alright, it also plays a critical role in pressure measurement, helping us understand and utilize fluid pressure in practical ways. Now mathematical proof. So consider a small prismatic element labeled A, B, C, D, E, F within a fluid at rest. Alright. So the figure 9.2 shows a fluid element in equilibrium, which is essential for proving Pascal's law. The prismatic element is very small, alright, allowing us to assume that every part of it is at the same depth from the liquid surface. This assumption simplifies our analysis because it means the pressure is uniform across the element. Since the element is at the same depth, the effect of gravity is same at all points within it. This uniformity is a key to understanding how pressure is transmitted equally in all directions. Remember, this is a fundamental aspect of Pascal's law. For clarity, we have enlarged the prismatic element in our figure 9.2. This enlargement helps us visualize the forces acting on it more clearly. So, uh, let's take a look at figure 9.2, which shows a prismatic fluid element in equilibrium. Notice how the pressure exerted by the fluid are represented on different faces of this element. This visual helps us understand how pressure is distributed in a fluid at rest. Now, let's delve into the details of pressure exerted by the fluid. The pressure PA, PB, and PC corresponding to the normal forces FA, FB, and FC on the respective faces BEFC, ADFC, and ADEB denoted by AA, AB, and AC. This is important because it shows us pressure acts uniformly in all directions in a fluid at rest. Now, uh, for equilibrium of the prismatic element, notice the figure showing a fluid element. This setup helps us understand how the forces act on different surfaces of the element. So, consider the horizontal equilibrium. The equation FB sine theta equal to FC shows us that the horizontal component of the force on one face of the element is balanced by the force on the opposite face. Next, we have the vertical equilibrium. The equation FB cos theta is equal to FA indicates that the vertical component of the force is balanced by the force on the top face of the element. From geometry, AB sin theta equal to AC, which shows the relationship between the areas of the faces in the horizontal direction. And equation AB cos theta is equal to AA computes our understanding of the geometric relationships in the vertical direction. Now, uh, here, prismatic fluid. So we can see FB upon AB is equal to FC divided by AC equal to FA divided by AA. This equation tells us that the pressure exerted by the fluid is same at all points on the prismatic element. Each term represents the force per unit area, which is the definition of pressure. So this gives us PB equal to PC equal to PA. Pascal's law statement. So pressure exerted is same in all directions in a fluid at rest. This confirms that pressure is scalar quantity. No direction can be assigned to it. Understanding this concept is crucial as it applies to various real-world applications such as hydraulic systems. Now let's summarize the concepts. So first, fluids differ from solids due to their ability to flow and lack of definite shape. So average pressure is equal to force upon area, defines pressure as force per unit area measured in Pascal. Density, mass upon volume, is the mass per unit volume, key property for fluid behavior. Common pressure units, 1 atm equal to 1.013 into 10 raised to the power 5 Pascal. 1 bar equal to 10 raised to the power 5 Pascal. 1 torr equal to 133 Pascal. Water density at 4 degrees Celsius is 1.0 into 10 raised to the power 3 kilogram per meter cube, serves as reference value. Pascal's law states pressure is confined, fluid is transmitted equally in all directions. For fluid element in equilibrium, PV equal to PC equal to PA proves pressure is a scalar quantity. Pressure exerted by fluid at rest is always normal to any surface it contacts. Both force, magnitude and area of the application determine pressure impact. Normal bones like femurs sustain pressure around 2 atmospheres during standing. So now we have a practice questions. First, what pressure will be exerted by a force of 100 Newton acting on an area of 2 square meters? A water tank has a height of 10 meters if water density is 1000 kg per meter cube. What is the pressure at the bottom of the tank due to the water column? Third, converts 2 atmosphere to Pascal. If an object has a mass of 500 gram and occupies a volume of 400 cubic centimeter, what is its density in kg per meter cube? A rectangular block floating in mercury has a surface area of 5 centimeter square in contact with the liquid. If the block weighs 6.8 Newton, what pressure does it exert on the mercury surface? Alright. Thank you for your attention.